Hello everyone, and welcome to this video where I'll be taking you through a sample problem on the objective identify the parametric equations of curves. In this video, I'm going to be going over one question from the Knewton.com site and their Knewton Alta homework system. And it's going to be a question involving some functions you don't typically see, or at least where I teach, you don't typically see these types of functions. So I want to talk about them a little bit. Those are hyperbolic functions. So let's get into it. All right, so here's the question. And I would highly recommend that if you know hyperbolic, the hyperbolic trig functions or the hyperbolic functions look like or behave like, maybe pause the video now and try to work this problem out yourself first before watching me do it, and then compare your work to mine, see how you're doing. But here we're asked to determine the type of basic curve the set of parametric equations represents. And we have our x-coordinate function, x of t equals 9 times the hyperbolic sine. That's what this SINH is. It's sinh, I've heard it called, hyperbolic sine of 9t. And the y-coordinate function, in terms of this parameter called t, y of t is 9 times the hyperbolic cosine. This is the COSH or Cosh, I've heard, or Cosh, I've also heard, of 9t. And, it's a multiple choice thing too when you're working on this in, Knewton Alta. Again, don't guess. Remember, the Knewton Alta is adaptive, so if you guess and get things wrong, it's just going to give you more and more problems to do. So don't guess. But we have is it a parabola? Will these equations, as the value of the parameter increases, will we trace out a parabola or a circle or an ellipse or a line or a hyperbola? Now you can already see I'm in instructor mode here. You can already see the hyperbola filled in. So we'll see when we eventually graph this thing that we'll have a hyperbola. Now, in other videos I've made recently on parametric equations, we've seen an example of parametric equations that trace out a parabola and a circle and an ellipse and a line. And so I wanted to do one that just did the hyperbola today. All right, so before I actually get into this, I want to discuss what is a hyperbolic sine and hyperbolic cosine. How are they defined? What do they look like? And then we'll come back to this. All right. So these are the hyperbolic trig functions or the just hyperbolic functions. And I'm not going to do all 6 of them, but just the hyperbolic sine and hyperbolic cosine that showed up in the question. So I'll just write a little general function notation here. Say f of x equals. Let's start off with that hyperbolic sine. So that was sin, and then with an h right after that. So it's just like the regular trig functions, but you'll see an h afterwards, right? So there's hyperbolic, sine, cosine, tangent, cotangent, secant, cosecant, and they all just have this h afterwards. All right, well, the hyperbolic sine can be defined in terms of exponential functions with base e. The hyperbolic sine, the sinh of x, say some input x, is the following. It's e to that x, all right, minus e to the opposite of x, or e to the negative x, and then this entire value that's divided by 2. All right, let me show you what this looks like in Desmos, that desmos.com free online graphing calculator. Okay, so here I am at desmos.com. Now let's go y equals here for the start of our function. And then SINH, hyperbolic sine of x. All right, you see this curve show up here. It looks almost like a cubic function. All right, and again, and I'll just put up that other definition I had too, where y was equal to the quantity e to the x minus e to the negative x, or the opposite of x, and then all this cut in half. And you see it's the very same thing, right? So another way to define this hyperbolic sine. Right, you can plug in values for x, and I think it's easier to evaluate this way. Again, you plug in 0, you get, 1 minus 1 divided by 2. Right, you plug, probably easier to use this version of the function when plotting points if you were trying to plot points by hand. All right, so that's hyperbolic sine. And then hyperbolic cosine, I'll call this g of x, right? Just some other function. Hyperbolic cosine, so again, C-O-S-H, or Cosh, I've heard, of some input x. It's very similar looking to hyperbolic sine. So the way you can calculate the hyperbolic cosine of a value of some input x is e to that x power plus e to the negative x, or e to the opposite of that x, and then divided by 2. All right, and let me show you this as well. And this will look more like a parabolic shape. They actually call this one a catenary, C-A-T-E-N-A-R-Y, like a hanging cable. A lot of hanging cables, equations for such cables, the shapes they take are given in terms of hyperbolic cosine, or some combination of hyperbolic sine and hyperbolic cosine. But let me take you back to Desmos here and show you hyperbolic cosine. So y equals that COSH of x. And like I said, you see it's almost like it looks like some parabolic shape. It's not exactly, though, parabolic, though. All right. And just that other definition involving the exponentials, right? Y equals the quantity e to the x plus e to the opposite of x, and then cut in half. And you see the very same curve there right on top of that other one, right? They're the same thing. Okay, so just wanted to get those out there and also show you one nice property, a nice relationship between hyperbolic sine and hyperbolic cosine. That's going to help us when we're working with, parametric equations involving them. All right, so let's say I were to square the hyperbolic sine. All right, I'm going to square both of these. Just like with the trig functions, you'll usually see the power you're raising it to right after the name. So what's hyperbolic sine squared? Well, that would square the numerator here. Now remember, when you take a binomial and square it, it's, first time, I'm doing foiling. It's e to the x times e to the x, whether it be e to the 2x, and then minus 2 of e to the x times e to the negative x. e to the x times e to the negative x is 1. So you just have minus 2 times 1. And then plus, you got negative e to the x times negative e to the x again, plus e to the negative 2x. Right, and then this gets divided by 4, right? 2 would also be squared in the denominator. And then I'll also square the hyperbolic cosine, Cosh squared or Cosh squared of x. So again, I'll take this fraction involving the exponential functions, square the numerator, square the denominator, and we'll get this hyperbolic cosine squared. So that'd be e to the 2x plus 2 times 1, so plus 2, and then plus e to the negative 2x. So again, very similar to the square of hyperbolic sine in the numerator. And then again, 4 in the denominator, right? Now, I'm going to take these two. We're going to subtract hyperbolic sine squared from hyperbolic cosine and see what happens, right? So hyperbolic cosine or Cosh squared of x, and then I subtract the hyperbolic sine squared, and look at what would happen. Again, they had the same denominator, right? It's going to be all over 4. And I'm taking the numerator from the hyperbolic cosine squared and subtracting every term from the hyperbolic sine squared. So you'd have e to the 2x minus e to the 2x. Those would go away. Then this e to the negative 2x minus e to the negative 2x. Those would go away as well. And I'd be left with 2 minus negative 2. Right? 2 minus negative 2 would be 2 plus 2. That's 4. And so we're left with 4 over 4, which is 1. And this is a nice property, a nice relationship between these hyperbolic sine and hyperbolic cosine. So do you remember for regular trig? Right, recall that when you were talking about circular functions, right, sine, cosine, tangent, the regular trig functions, the cosine of some value squared plus the sine of that same value squared was always equal to 1. Right, the plus. Well, with these hyperbolic functions, it's a minus, right? The hyperbolic cosine squared minus hyperbolic sine squared will always be equal to 1. And that's what I'm going to use to help me out with this problem that we're given in Newton here. All right, so back to the question. And we have x is 9 times this hyperbolic sine of 9t, and y, the y coordinate of any location we're at, is 9 times the hyperbolic cosine of 9t. So I'm going to go back to my paper and write that out. So I'm just going to write it this way as x equals, I know it's x of t, but I'm going to write it this way for a reason you'll see in a minute. So the x coordinate was, again, 9 times hyperbolic sine of 9t, and y equals 9 times the hyperbolic cosine of 9t. And they didn't give us a range of values for t, so I would just imagine it would be whatever, t can be any real number. All right. So let's just assume t can be any real number here. There's nothing that'll make hyperbolic sine or hyperbolic cosine undefined, as you saw with the exponential definition. So let's just assume t can be any real number, and it'll trace out whatever curve we're trying to look at on the xy plane. So what I'm about to do is called eliminating the parameter. Right? The parameter is this letter t that the x and y coordinate depend on. I'm going to try to set it up so we get a relationship between these that can enable me to write an equation for the curve without t. So when you have your trig functions or hyperbolic functions like these, I would highly suggest solving for them. So in this first equation, see if I solve for this hyperbolic sine, we'd have the sine, the hyperbolic sine, the sinh of 9t is going to be equal to, the x coordinate of whatever location I'm at divided by 9. I'm dividing by 9 to solve for the hyperbolic sine of 9t. And then similarly, in this equation, I'm going to solve for the hyperbolic cosine of 9t, the Cosh of 9t. And that's going to be giving me the y coordinate of any location I'm at divided by 9. And then just recall from the previous page that if I take the hyperbolic cosine of, anything, the little box there, something, and square that, and then subtract the hyperbolic sine of that same thing, right? Which, both of these have the same argument, right? 9t are both inside the hyperbolic cosine and sine here. Square that, and it's always going to be equal to 1. This is the property I wrote up on the last page. So, the hyperbolic cosine of 9t squared minus the hyperbolic sine of 9t squared must be equal to 1. And we have expression for these without the parameter, right? Like I said, this is called eliminating the parameter, right? An equation for the curve without parameter, which is t here. So the hyperbolic cosine of 9t, that is replaced with y divided by 9. And that's being squared. Minus the hyperbolic sine of 9t replaced with x over 9. Also being squared equals 1. And then when I actually square this stuff, this is y squared over 81 minus x squared over 81 equals 1. And this is clearly, remember, I'm hoping you remember this from like pre-calculus, the equation of a hyperbola in standard form, right? And I'll sketch the hyperbola over here, and then we'll actually go to Desmos and take a look at it a little better. So here's a rough XY plane. So remember, this would be a hyperbola with a center at the origin, vertices 9 units above and below, right? This is going to have branches of the hyperbola opening up and down. This will be a vertical because it's y squared minus the x squared. So 0, 9, 0, negative 9 are the vertices. Okay, and then you got your asymptotes, which, being that these are both 81 here, you got a rise of 9 and a run of 9. So I'll make a little box here with 9 up, 9 down, 9 left, 9 right from center, and then hopefully this all rings a bell, graphing hyperbolas. And then through the corners of this box are the asymptotes, right, that run through the center and the corners of this box I just set up. And none of these, the box and the asymptotes and the center, none of these are actually part of the hyperbola. And then the rest of it is from the vertices here, 0, 9 and 0, negative 9. I draw out the branches, these kind of U-shape, almost parabola shapes that oppose each other and approach these asymptotes as you get further from the center. I shouldn't be putting the arrows on. Right there. That's what we're going to be looking at. Because again, I shouldn't have been putting the arrows on because technically we should have the arrows, going the way that the point is moving as t increases. Right? So like when t is 0, we saw earlier the sinh of 0, hyperbolic sine of 0 is 0, and cosine of 0, hyperbolic cosine of 0 is 1. So we'd be at this point here when t is 0. And as the value of t increased, basically this would be a positive values. Like it's going to trace out that way up there, and then we'd have to go to negative values of t down here. Like I'll show you in Desmos, right? So I'll put it up in parametric form, non-parametric form, right? This form down here where I got rid of the parameter, and we'll see how this hyperbola is traced out. We'll see its orientation. All right, so back to Desmos. So let's get rid of this. So yeah, first I'm going to put up the parametric equations. So remember to do that, you got to put in as an ordered pair. So the x coordinate was 9 times the hyperbolic sine of 9t. And then the y coordinate, 9 times the hyperbolic cosine of 9t. And I'm just going to go from like negative 10 to 10 right here. Like I said, they didn't really, in the problem, they didn't give us a range for t. So I'm going to go negative 10 to 10. And you'll see when I zoom out here. Okay, so yeah, I guess based on the fact that this is a positive 9 in front and positive 9 in front, remember Coach, we saw the graph of Coach earlier, that was always positive. So when you do 9 times a positive value, you're going to have a positive y coordinate the whole time. And sinh looked like a cubic, so I had negative, hyperbolic sine was negative to the left of 0 and positive to the right of 0, had positive outputs. So you'll have negative x coordinates for negative values of t and positive x coordinates for positive values of t. So yeah, you're only getting the upper half of this hyperbola. All right, so my paper drawing here, you're not getting this bottom half. And that's solely because of the way these hyperbolic functions are restricted. And so this y coordinate's always going to be positive. This is something I probably should have pointed out earlier. But still, we see that in our Desmos drawing. Because hyperbolic cosine is always positive, and this is times 9, the y coordinate's always positive, so it's got to be this upper branch. All right, and then we'll see the trace too. We're going to see the trace, for negative values of t will be over here, and then as t increases, we'll get to positive values of t will give me positive x coordinates. And that's it, right? We're only going to trace out this upper branch. Now, if we want to see the tracing out of this upper branch, right? Because again, you got a bunch of it right here. Remember how I did this in previous videos? If you haven't seen it, you're seeing it again here. If you want to see how it's traced out, the orientation of the curve, just replace t, which is the typical parameter, with any other letter. So 9 times, the hyperbolic sine of 9s, I'll use s for t, comma, and then 9 times the hyperbolic cosine of 9s. And instead of asking for a range of values for s like it did for t, it's just asking you to put in a slider. So I put in a slider, so it's negative 10 to 10. I'll label the points, and you can see, let me move it so it's actually on screen. When s equals 0, right, when t equals 0, s equals 0, we're at the point 0, 9. And I'm going to make it real slow, change the playing speed real slow so we can see what happens when I hit play. It's left to right. Right. Let me back this up again. As s increases, you'll see the point eventually traced from left to right. See that going on there, right? That's the orientation of the curve. I know it kind of went by pretty quickly, but this branch of the hyperbola is being traced out from left to right, and that's all that's being traced out. And then let me put up the equation of the hyperbola that we had after eliminating the parameter, right? We had y squared over 81 minus x squared over 81 equals 1. You see that pop right on top of that. The only difference is the bottom branch is there, right? There's bottom branch with negative y values. But like I said, Cosh, hyperbolic cosine is not negative. So 9 times the hyperbolic cosine won't be negative. You're going to have part of this with only positive y coordinates. So that's why you're only getting that top branch. Hopefully that's clear. All right. Still, after all that, you didn't have to go through all that, right? I didn't need to do all that. You might just in the future recognize, hey, both of these are, hyperbolic functions, so it's probably going to be tracing out a hyperbola. Right? It's very quick and simple. I just kind of added more to it to explain things that were going on, and hopefully I explained them well enough. All right, so hopefully watching me go through this here. And again, previous videos where I went over parametric equations where we saw an example of a parabola, circle, ellipse, a line, and a line help you when you're working on this stuff on your own. And thank you very much for watching.